Well, hello everyone. This is Chris back again with the Ancient Scholar, and still in the hotel room, so still recording through an alternative format, and I hope you guys are getting something out of this. I do apologize if you're finding it difficult to get anything out of this format, and go ahead and let me know if this isn't helpful, and maybe I can shoot some other videos or some newer videos on the standard, the older format. So what I'm going to do is I'm just going to talk about P2 or row 2 or density. This will be density part 2. So I think where we'd left off is we were just going to talk about calculating the density of hydrogen. We already talked about Avogadro's law, the mole, the 22.4 liters per mole at standard temperature and pressure conditions, standard atmospheric conditions, being the volume of any ideal gas. And then it was just a matter of finding what the atomic mass was and dividing it by that 22.4. And we were just going to do that with hydrogen, H2, in its gaseous phase. And this is where we need to be very careful, because we know that hydrogen, atomic hydrogen, is just one atom, whereas H2 is a diatomic hydrogen, or a molecule of hydrogen, molecular hydrogen, in its gaseous phase. So that's actually going to be 2 divided by 22.4 liters. So basically what that says is if I have 1 mole of hydrogen, H2 gas, that mole is going to have a mass of 2 grams and a volume of 22.4 liters. So what we do is if we divide that mass by the volume, that will give us our rho. So you whip your calculator out and you just simply go 2 divided by 22.4, and rounding to just 3 significant digits, that should give us 0.089, and the unit is grams per liter. 0.089 grams per liter. That is the density of molecular hydrogen gas. As we could probably guess, that is a very low density. That is one of the lowest density gas that you'll ever run across. So we can kind of use this as our baseline and say, look, that is about as low a density as you're going to get when talking about gases. So let's just go ahead and look at a couple more gases. Let's go ahead and look at helium now. Helium. So the question we need to ask ourselves is, does helium, is it a diatomic? Is it 2 atoms of helium in its gaseous phase? Well, if we remember, helium has 2 electrons, has two protons, 2 electrons, and under normal circumstances, those electrons will inhabit a 1s orbital. The 1s orbital can only hold 2 electrons, therefore that orbital is full, and helium is actually a happy atom. It doesn't need to bond with other atoms to be stable for its electrons to achieve stability. It has what we call duet stability versus octet stability, what we're all familiar with. But really, helium pretty much acts like an atom that has met its octet rule. And if you don't know what the octet rule is, you can go ahead and review some of the basic chemistry concepts, but if you don't, it's all right. Just for now, helium is a happy atom. It doesn't need to bond with anything. It's inert. It is chemically inert. So helium gas is just a helium atom. It doesn't need to take He2. It's just helium all by itself. So in that case, we simply plug in the atomic mass for helium, which is 4 divided by 22.4. And that should give us 0.179, rounding to 3 significant digits, grams per liter. Grams per liter. And we compare that to hydrogen, so this is helium. We compare that to hydrogen in its gaseous phase, that's 0.089 grams per liter. Grams per liter. And you can definitely tell there's more mass here, and certainly this number is larger than this number. So our math seems to be working intuitively, and that's a good thing. Okay, let's go ahead and look at molecular oxygen, O2. Look on the periodic table of elements. Oxygen is 16. Its mass number is 16. It has an atomic number of 8. Okay, so we just plug 16 in, right? Ah ha ha. Hopefully I didn't trick anybody, because we're talking about molecular oxygen, which is 2 oxygen atoms. So it's actually going to be 32 divided by 22.4. We do the math on that, and that should give you 1.43 grams per liter. You can see this is significantly more dense than hydrogen, helium. Okay, that's oxygen. Let's go ahead and look at nitrogen. And nitrogen, which is N on the periodic table of elements. It is in period 2, the second row, so we know its electrons are valence electrons are p orbitals. That's not really important for this conversation. What is important is that nitrogen has an atomic mass number of 14. And is nitrogen what we call one of those inert gases like helium? No, all the inert gases are all the way on the very right of the periodic table of elements. So if you look at the periodic table, and it looks something like this, something like that. All the elements on this row on the very right in your group 8 elements, those are all the inert gases. The inert gases. So nitrogen is right about there, give or take, and so it's certainly not. So we also have dinitrogen in its gaseous phase, or N2, and that is 2 nitrogen gases, 2 nitrogen atoms bound in a triple covalent bond. So that's what it kind of looks like. So if nitrogen N by itself is 14, the density of nitrogen gas, or diatomic nitrogen, is going to be 28 divided by 22.4. And that should give us 1.25 grams per liter. Grams per liter. So gas density really is just that easy. Okay, well, let's go ahead, and I know, we don't want to make it any more difficult, but let's make it a little more difficult, because we don't always necessarily deal with one gas in respiratory therapy or even in healthcare medicine. We generally deal with gas mixtures. Ooh, forgot an E. There we go, gas mixtures. So the formula for gas mixtures is we need to know the percentage of a certain gas in the mix. And what we do is we'll just go with 2 gases for now. Just 2 gases. What we'll do is we'll take the weight, or the mass of gas 1 times the percent, and we'll add that to the mass of gas 2 times the percent divided by 22.4 liters. That's our basic formula. So let me just go ahead and say that I have a mix, and it is 50% helium and 50% hydrogen gas, both in their gas phase. Okay? And I want to know what the total density of the mix is. Okay? So let's go ahead and plug that into our formula. So let's just make helium gas 1. Okay, so the mass, helium, is 4, and it's 50%, 4 times 0.5 plus And then we'll do our hydrogen, 2 times 0.5 divided by 22.4 liters, okay? So, what is 4 times 0.5? 4 times 0.5 is, and you should be able to just plug this into your calculator, just kind of do it in your head, 0.5, 1, 1.5, 2. So 2 plus 2 times 0.5, well, that's easy enough. That's 1 divided by 22.4. All right, so 2 plus 1 is 3 divided by 22.4. And that gives us 0.134 grams per liter. All right, so there we have the density of the gas mix. So let's just go ahead and mix it up a little more, and let's now say that I have 90% helium and 10% hydrogen. So I'd expect this mix to be a little more dense than the last mix, so that's easy enough. All I do is I go, for my helium, I go 4 times 0.9 plus 2 times 0.1. Divide all that by 22.4, right? That gives me 3.6 over on this side, plus 0.2, 3.8 divided by 22.4, and that should give me 0.17 grams per liter. All right, gas mixes, that easy. Okay, I think on the next video we'll actually start talking about why this is even relevant, where this is helpful, and I'll give you a hint. It may have something to do with conditions where I have increased airway resistance. Maybe I have an obstruction, and maybe I need to make special mixes of gases that I can give to get around that obstruction and to decrease the work of breathing. So that we'll leave for another discussion. Thanks for hanging in there, guys. Take care.